Specific volume, which is the reciprocal of density, is another aspect of the polymer that is important. Because of its high coefficient of thermal expansion, it experiences large changes relatively in volume, accordingly also sets up thermal stresses within the polymer. In the case of an ideal gas, you remember from high school chemistry or physics, PV equals nRT. So that is basically what you see as a plot in the case of polymers as opposed to ideal gases, where the specific volume, centimeter cube per gram, is plotted as a function of temperature. You increase the temperature, you increase the specific volume. Increase the pressure, you reduce the specific volume. So this variation of PV equals to nRT is represented by the dual domain Tate equation of how the specific volume changes as a function of temperature and pressure. Because it's a large molecular weight material with entanglements, chemical interactions, and so on, it's different from an ideal gas, and the nature of this behavior also changes. This is very useful for describing shrinkage and other attributes as well of the polymer as it's being printed. When you begin to add fillers into the polymer matrix, the specific volume goes down with increase in filler content. In other words, density goes up. That behavior can change if you're dealing with hollow particles, but only for solid particles, this is typical fillers that you come across in polymer processing and 3D printing. The direct rule of mixtures is useful for describing how the specific volume of the filled material, the composite, changes as a function of the weight fraction, just defined by X of the filler. XF is for the filler, XP is for the polymer. These symbols have to be adjusted accordingly. There is not as much particle size dependence in this specific volume dependence on filler content as you saw in the case of viscosity. It's not just as pronounced. General trend is specific volume reduces with increasing filler content. Density, which is a reciprocal of specific volume, is a good thing to measure as well because it's a design parameter. Aerospace, automotive components, you want to make sure that fuel efficiency is taken into account by controlling the density of the material. Here, density as a function of weight fraction is plotted for a few ceramic filled PTFE materials. You remember what is PTFE? The inverse rule of mixtures allows you to represent this behavior fairly well. Again, in this case, XP refers to P refers to powder, B refers to binder, which is a polymeric phase. The density of the composite increases with the weight fraction. If you used volume fraction as a weighting parameter, then you can use the direct rule of mixtures as opposed to the inverse rule of mixtures. Typical physical properties of thermoplastics, to recap. Compared to metals, they are lower in density, typically lower than most ceramics as well. They have a much higher coefficient of thermal expansion than metals or ceramics. They have much lower temperatures for melting typically. There are, of course, many examples of metals that have low melting points. For instance, mercury is a liquid at room temperature, right? There are other alloys such as solder alloys that melt lower than some high temperature polymers as well. They have a higher specific heat. Individual molecules have many degrees of freedom, and as a result, the ability to store thermal energy is higher, and that's why they're 2 to 4 times those of metals and ceramics. They also have a lower thermal conductivity typically, so they are about 3 orders of magnitude lower than metals, and so they are regarded as insulators. The majority of them are also insulating in electrical properties, though there are some changes and differences over there as well. Let's take a look at some thermal properties as a function of filler content. Since polymers have a higher heat capacity than inorganic materials such as metals or ceramics as fillers, you can imagine that specific heat will go down as a function of increasing filler content, as shown here for a wide range of fillers, both metals as well as glass fibers and ceramic. A modified rule of mixtures relates heat capacity as a function of the weight fraction of the filler. This changes to some extent based on the shape of the filler as well, which was not the case for specific volume. But generally, you increase the filler content, you reduce the specific heat. Thermal conductivity as well can change as you change the filler content, because polymer is insulating If you use a metallic filler, you will increase the thermal conductivity. You can increase the thermal conductivity with ceramics as well, which are also insulating, but tend to be higher than those for polymer. So here's an example of a couple of different thermally conducting ceramics: boron nitride, silicon carbide, and also aluminum as a metal example. And you can see thermal conductivity goes up as filler volume percent goes up. The Bruggen model allows you to describe this and model this thermal conductivity, where Phi again is a volume fraction of the powder filler. These design equations are useful to be able to a priori predict what material composition will be useful for introducing some functional properties. The viscosity behavior then also shows how you might be able to compensate for processability changes as you begin to dial in certain functional attributes such as thermal conductivity. Generally, thermal conductivity increases as you increase the filler content. We looked at heat capacity and thermal conductivity. Thermal diffusivity is the ratio of the thermal conductivity to the volumetric specific heat, and is usually considered in many heat transfer analysis problems when you begin to design a product for functionality in terms of thermal properties. The units of thermal diffusivity is meter square per second. Generally, thermal diffusivity is very high in metals.